Chapter 3 is all about how to solve systems of equations and apply them toward applications. Now we're going to start by showing how we can solve systems using graphs and tables. And then a little later on in this chapter, we're going to show some other algebraic ways of solving these systems. Now first we should talk about what is a system of equations. So system of equations is when we have two equations, as we can see we have here. So there's the first equation, and there's the second equation. And the equations have two variables. So notice you have x and a y in that equation and x and y in the other one. So that's called a two-dimensional system of equations, where we have two variables and two equations. And when we consider the two equations together as a group, it's called a system of equations. Now our job is to find a solution of this system. And the process of finding a solution is called solving the system. In order to solve the system, we need to find an ordered pair, x comma y, that makes both equations true. And the key word there is both. So the same numbers, x and y, have to make each one of the two equations in this original system true. Now one way of solving this kind of a system is by graphing. And what we'll do to solve it by graphing is we'll take each equation in the system one at a time and we'll graph the equation. And it should come out to be a straight line. And then once we've graphed both of the two lines together on the same axes, we'll determine the point where they intersect. And the ordered pair x comma y, where the two lines intersect, will be the solution of the system. Now in order to graph these two equations, we'll first have to put them in the form y equals mx plus b. So I'm going to take the first equation, 2x minus 3y equals negative 6, and I'm going to subtract 2x from both sides, and that will give me negative 3y equals negative 2x minus 6, and then divide both sides by negative 3, and our equation would end up being y equals, it would actually be positive 2/3 because that's a negative divided by another negative, x, and then plus, because that's also two negatives divided, 2. Now I'm going to graph this line using the slope and the y-intercept. Now remember, this number at the end here, plus 2, is the y-intercept. So we know that we have a point right at 2 on the y-axis. So I'm going to put a point right there. And then the number that's multiplied in front of the x, which is your m, is your slope. So that really means, if we interpret that, that you would go up 2 and 3 to the right. So if I take that point and I move up 2 and then 3 to the right, that should give me another point on that line. Now we can also move down 2 and back 3 to the left, and that would also bring us to another point on the line. So I'll plot that one as well. Okay, so we've got that first line graph now. So now I'm going to do the same thing with the second equation. So we have x plus 3y equals negative 3, and subtract x from both sides. So 3y equals negative x minus 3, and then divide through by 3, and we get y equals be negative 1/3 for the slope, x minus 1. Now in this case, the y-intercept would be negative 1, so we know that the line would intersect the y-axis right here at negative 1, and the slope is negative 1/3. Now usually when we have a fraction like that, we'll put the negative sign in the numerator, so it's negative 1/3. That really means down 1 and to the right 3. So we'll go from here down 1 and to the right 3, and then that'll bring us to another point on the graph. And we could also go up 1 and back to the left 3. So if we did that, brings us right over to here to that same exact point, in fact. And so you can see what that line is now going to look like. And then the solution would be the ordered pair where the two lines intersect. And that looks like it's at -3, 0. So -3 for the x and 0 for the y. And that would actually be the solution to this system. Now if you want, you can substitute -3 in for x and 0 in for y in each one of the two original equations, and they both should come out to be true statements. And they do, so it does check. In this next example, I'm going to show you how you can use your graphing calculator to find the point of intersection. A lot of times the lines might cross at fractions or decimals, and it's going to be hard to tell from the graph exactly where they cross. And that's where the calculator comes in handy. Now we'd start out the same way. We have to take each equation and write it in the form y equals mx plus b. So I'll start with the top one, and I'm going to subtract 4x from both sides, and then divide everything by -3. And so that equation ends up coming out to be y equals 4/3 x minus 13/3. Now if I do a similar thing with the second equation, we've got 2x plus 5y equals 5, and we'd subtract 2x from both sides. So 5y equals -2x plus 5, and then we'll divide through by 5. And for that one we end up with y equals -2/5 x plus 1. Okay, now we'd put these into our calculator, and so under y1 you'd enter your first equation. Now put the 4/3 inside parentheses, and then times x, and then minus 13/3. And then do the same thing for the second equation. Again, always put the slope in parentheses in your calculator when it's a fraction. So -2/5 in parentheses times x plus 1. And then I'm going to graph it just using a zoom standard, which is 6. So you just press the 6 key. Remember, that just is your basic window that goes from -10 to 10 in both directions. And we're looking for this point of intersection here. So if we use second and then trace, we want to choose option 5 here where it says intersect. So you can just hit the 5 key. And then when it says first curve, all you have to do is hit enter. When it says second curve, just hit enter again. But when it says guess, you actually want to use your right or left arrow key to move that cursor close to the point of intersection and then hit enter. And notice the calculator displays both the x and the y coordinate of that point of intersection. And they're decimals, and you'd have to round them off. So I'm just going to round those off to, for the x, we'll round it off to the nearest hundredth. So for the x, we'll say 3.08. And for the y would be -0.23. And that'd be your solution for this system. Once again, you do have the ability to check that answer. Just substitute the 3.08 in for x and the negative 0.23 and for y, and do it in both of these two equations, and then they should both come out to be really close to true. They might not be quite perfect here since we've rounded the answers, but they should be very close, and that would show that the answer is right. Now there's two special cases that we need to talk about. The first case is when the two lines are parallel. Now if the two lines are parallel, obviously there's no point of intersection because parallel lines never cross. So therefore there's going to be no solution either. So your answer in this case would be that there's no solution. And often when there's no solution in this case, the system is said to be inconsistent. So inconsistent is a code word that means there's no solution and that the lines are parallel. Now the second special case is when the two lines end up being the exact same line, meaning when you graph them, one's right on top of the other. Now in this case, there's really an infinite number of points of intersection because every single point on the line is a point of intersection since both lines are right on top of each other. So there are infinite solutions. And as you've probably guessed, there's a code word for this as well. In this situation, the system is called dependent. So dependent is a word that you use when the two lines are exactly the same, and so there's an infinite number of solutions. Okay, so let's take a look at this example. We have y equals negative 3x plus 2 and y equals negative 3x minus 5. Now you can see both these lines have a slope of negative 3. So the slopes are the same. That tells us that the lines are parallel, or either that or they're the same line. But if we compare the y-intercepts, you see the y-intercepts are different. So they have the same slope, but different y-intercepts. And if that's the case, then they would have to be parallel. So these lines are parallel, and so we would say that this system is inconsistent. Now let's look at this next example. Now the first equation is y equals 2x plus 1, and that's a nice simple form, y equals mx plus b. The second equation is not in the form y equals mx plus b, so I'm going to put it into that form. So we would have, the first thing to do would be distribute the parentheses. So we'd have 6x plus 2 on the right side of the equation. And then add 1 to both sides. So that would give us 3y equals 6x plus 3. And then divide everything by 3. And that ends up giving us y equals 2x plus 1. Now notice that answer, y equals 2x plus 1, is the same as the first equation. They're the exact same equations. So since they're exact same equation, they have the same slope and the same y-intercept, they're the same line. And so this is a case where every point on the line would be a solution, and so we would call that dependent. Okay, now let's look at how we can use tables to solve systems. Now in a table, well, if we're given the various different x coordinates, you know, in this top row, and then we have one equation in the second row and the other equation in the third row. And what we really want to do is compare the y values to find where they're the same. Now here they're not the same because you have 11 and negative 25, so the y values aren't the same. Here the y values are not the same either. Here they're still not the same, 1 and negative 11. Here, if you can see negative 4 and negative 4, they are the same there. That's the key right there. Because the y values are equal right there. So if the y values are equal, that will represent the solution to the system. Now the actual order pair of the solution, the x coordinate would of course be 3, because you can see the x is 3 there, and the y coordinate would be -4, which is the same for both of the two equations. And that would be the solution. Now in the second example, we're going to estimate the solution. We may not be able to find it exactly, but we're going to try to estimate it a little bit. So again, we're looking at the y values, trying to see where they're the same. 30 and 2, they're not anywhere near the same. 27 and 7 aren't anywhere near the same either. 24 and 12, they're still pretty far away. Now by the time we get to 21 and 17, they're starting to get kind of close. But the f of x is still bigger than the g of x. 21 is bigger than 17. And if we go up one more, they're still kind of close, but now they've switched. F of x is only 18 and g of x is bigger. So somewhere between an x of 3 and an x of 4, these crossed, or in other words, they met. And so we'd probably estimate that, let's just say we estimate that at a 3.5. So if we said 3.5 for the x, and what do you think the y value would be at that point? Well, it's certainly got to be, well, it's got to be more than 17, because it's got to be between 17 and 22. And it's also got to be between 18 and 21. So it could be 19, 20, something like that. Okay, maybe 19 and a half. So you could estimate that that would be about your solution there, but that's the best you could do in this kind of a table, because the y value is never matched up exactly. So you just kind of have to find out where they come close to matching up, and that's in this range here. Now I'd like to go over an application that deals with a system of equations. In this table, it shows the number of landline calls, and these are measured in billions, and also wireless calls for 411 calls, which is public assistance. And we're going to define our variables, and we're going to let t equal the number of years after the year 2000. And we'll let the variable y stand for the number of calls in billions. So I'm actually going to put a new column in here for t. So t would be 1, 2, 3, 4, 5, because that's the number of years after 2000. And then the landline, that would be your y. You actually have two different y's, so I'll call that y1. And your wireless is another y, so y2. Now I'd like to start by making a scatter plot of this data on my calculator. And notice what I've done is in the list L1, I've put in the different values of t. So 1, 2, 3, 4, 5. And in L2, I entered in the landline information. And in L3, I've entered in the wireless information. So I've got all the data right there in those three columns. Now, I want to really make two scatter plots. I want to plot L1 versus L2, which would show me a scatter plot of the landline information. And I also want to plot L1 versus L3, which will give me the wireless information. So this would need to be set up as two different graphs on a calculator, and I'll show you how that works. Let's see here. What we would do is we'd go ahead and press second stat plot, and plot 1 is already on, so we can hit enter, and you see it's on. It's set to a scatter plot for L1 and L2. So that one's all set up to do the first one. So we do second stat plot again. I actually want to go down to plot 2 and turn that one on as well. So I'm going to turn that on. It's set to a scatter plot. Now I want that to go L1 and L3. So that L2 has to get changed to an L3. If you do second and then the number 3, it'll change it to the L3. And then if we do a zoom 9, it'll graph both sets of data together. So that gives you a pretty good picture that they both look like they're more or less straight line patterns, and they will cross at some point out in the future. They haven't crossed yet, but one's decreasing and the other one's increasing, so we should be able to find that they cross. Now in this case, we don't have the equations given to us, so we're going to have to find the equations ourselves. So in other words, we're going to have to find the equation of a straight line that connects these points, and then we're going to have to find another equation of a straight line that connects these set of points. Now it looks to me, if I were to use the very first point and the very last point and connect those with a straight line, that would do a pretty good job of modeling that top set of data. And if I did the same thing in the second case, the very first point and the very last point, that again would do a very good job modeling the bottom set of data. So that's what I'm going to do. I'm going to use the very first point and the very last point. So that means I'm going to use, for the landline equation, I'll use 1, 4.6 and 5, 4.2. as my 2 points, and I'll find the equation of the line that passes through those. And then when I do it again for the wireless, I'll use the y coordinate over here instead of the landline one. And so those would be the points 1, 1.3, and 5, 2. So let me start with the landline information. Again, I've chosen the very first order pair and the very last order pair for that set of data. And I'm going to calculate the slope. So the slope would be 4.2 minus 4.6 divided by 5 minus 1. And when you work that out, you can try it on your calculator. It comes out to be negative 0.1. And then I'll use one of these two original points. I'll pick the first one along with my slope, and then I'll use point slope form. Y minus y1 equals m times x minus x1. And if we substitute the information in, we get y minus 4.6 equals negative 0.1 times x minus 1. And then we'll distribute. So we get negative 0.1x plus 0.1, and then add 4.6 to both sides. So we end up with y equals negative 0.1x plus 4.7. Now, I'm going to have to clear this screen to leave myself room to create the other equation, but keep that equation in mind. We have y equals negative 0.1x plus 4.7, and that should represent the landline data pretty well. Now I'll do the same thing for the wireless data. Again, this is the very first order pair for the wireless, and this is the last order pair. And so I'll calculate the slope. So the slope would be 2 minus 1.3 divided by 5 minus 1. That works out to be 0.175. And then I'll use this first point right here along with the slope, and then we'll do y minus y1 equals m times x minus x1, which would be y minus 1.3 equals 0.175 times x minus 1, and then we'll distribute. And then we'll add 1.3 to both sides of the equation, and we get y equals 0.175x plus 1.125. So now it's time to graph both equations and use our calculator to determine where they intersect, which is the solution that we're looking for. So we'll start by pressing the y equals key, and we'll enter in that first equation that we came up with a couple minutes ago. So that's negative 0.1x plus 4.7. And then we put our second equation in, which is the one we just found, 0.175x plus 1.125. And then just hit the graph key. And that will show the two lines plotted through the data, and you can see they do represent it quite well. Now, we need to see farther to the right, so we'll change our window, and if we raise our x max up to a bigger number, we'll see farther to the right. So I'm going to change that to a 10 and then just hit graph again. And that shows farther to the right because I want to see where they cross. I still didn't get it quite far enough, so I'm going to go back to the window and then change that to a 15. And now they do cross, so I'm looking for this point of intersection. So we do second and then trace and then intersect, which is number 5. And then for first curve, just hit enter, and second curve, hit enter. And for the guess, move that cursor up close, and then hit enter one last time. And there's the intersection point right there. X equals 13, and Y equals 3.4. So that would be our solution. Now remember, in our case, we didn't use X, we used T. So T would be 13, and that's 13 years after the year 2000. That would make it 2013. And the Y value is 3.4. And that's telling us that there were 3.4 billion calls. And both for landline and wireless. So they were both the same in 2013. So both of them would have had 3.4 billion calls.